Welcome to A-Level and AP Physics. In today's lesson, we will discuss important past paper questions on radioactivity from May-June 2020. Our first question is from May-June 2020, paper 1-1. For this question, it is given to us that an element has two isotopic forms, and question is asking us what are the nuclear arrangements of these two isotopes. Simply, you need to understand what is isotope in order to answer this question. First of all, let's try to understand a little bit about isotope. Isotopes, simply, these are the atoms of the same element with same atomic number. So we can write down they have the same atomic number, means Z, same atomic number, and they have different mass numbers. So we can write down they have different mass number or they have different nucleon number. The mass number is the same as nucleon number, so we can also write down here mass number is the same as nucleon number. So nucleon number. Now the next thing we need to understand is that same atomic number also means that same number of protons. So the next thing you also need to understand, same atomic number means that same number of protons, and different mass number. If atomic number is the same, it means two nuclei, they have different number of neutrons. So we can write down here different number of neutrons. So this is what you need to understand in order to answer this question. Let's look at the first one. If for option A, it is given to us they have different nucleon numbers, so that is right. Different proton number, that is wrong. It has to be same. So this is not correct option. Now if we move to next one, it is given to us they have different nucleon numbers and same proton number, so this is correct option. Now if we go to next one, it's telling you they have the same nucleon number, same nucleon, so this is wrong. Different nucleon number and the same proton number, this is right, but this is wrong. They have the same nucleon number, this is again wrong, and different proton number, that is also wrong. So our answer for this question is B. That's the answer. For this question, it is given to us that a hadron has a charge plus E. Hadron, when we talk about hadron, it means we are talking about heavier particles. So this is heavier, H for heavier. Plus E. E is the elementary charge. This means this is equal to the charge on single electron or single proton. Question is asking us which combination of up and down quarks could form this hadron, a hadron which has charge equal to plus E. Now first of all, let's try to understand what is the charge on up quark. Each up quark, it has charge plus 2 by 3 E. Each down quark, it has charge equal to minus 1 by 3 E, means 1/3 of the charge on single electron. For this one, we need to find out the charge on each combination. If we look at this one, we have 3 quarks, so simply we need to add the charge on each quark. So simply we have to add the charge on each quark. Now here, if we add the charge on each quarks, our final answer in this case will be equal to minus E. So it means this combination will not give charge equal to this. So this is not correct option. If we move on to B now, we can also find out the charge on this combination. Here we have 1 up quark, so this is 2 by 3 E, plus we have down quark. The charge on down quark is minus 1 by 3 E, and plus the charge on next down quark, that is also minus 1 by 3 E. If we add these charge together, means the charge on up quark and charge on 2 down quarks, we will get 0. So this is also not equal to E. So it means option B is also not correct option. If we go to option C now, for option C we can also find out the total charge, and that is plus 2 by 3e, means this is the charge on single up quark, and we have two up quarks, so plus again 2 by 3e plus down quark minus 1 over 3e. If we add all these charges together, in this case our final answer is plus 1e, and that is the charge on this hadron. So this is correct option, means that's the answer. Let's check D now. For D, if we check this, we have 3 up quarks, so simply we can say the charge will be 3 times 2 by 3e. So if we simplify this, our final answer in this case is plus 2e. So this is also not the charge on this hadron, so this is also not correct option. So C, that's the answer. This is the answer. This question is from May-June 2020 paper 1-2. Question number 39. For question 39, it is given to us that an unstable nucleus goes through successive decays to become a final stable nucleus. It is also given to us that initial nucleus and final nucleus, they are isotopes of each other. Isotopes, it means that initial nucleus and final nucleus, they have the same proton number. So they have same proton number, same number of protons. Same number of protons means final nucleus and initial nucleus, they have the same number of protons. So this is the main point we need to understand. They can have different number of neutrons, so they can have different number of neutrons, or they can have different mass number. Different number of neutrons they have, but they have the same number of protons. Different number of neutrons also means that the mass number is different or nucleon number is different. So we can also write down here mass number is different. So the mass number is different. So this is what we need to understand to answer this question. It is also given to us alpha decay and beta minus decay. Let's try to understand alpha decay and beta minus decay. First of all, let's try to understand what is alpha decay. Let's say we have X nucleus, its atomic number is Z and mass number is A. It decays and emits alpha particle. So we have new nucleus here, so it emits one alpha particle. So in this case, atomic number means the proton number will decrease by 2 and the mass number will decrease by 4. But for this question, we no need to worry about mass number, because isotopes, they can have different mass number. So from here, simply we need to understand in an alpha decay, proton number decreases by 2. Proton number decreases by 2. So this is the main concept you need to understand for alpha decay. Let's write down here beta minus decay. We also need to understand beta minus decay. Let's say we have X nucleus and this nucleus decays to another nucleus by emitting beta particle. By emitting beta particle means beta minus. So this is minus beta minus. Let's say the atomic number of this nucleus is Z and the mass number is A. Here we need to understand atomic number of this new nucleus. This has to increase by 1, Z plus 1. So then on both sides proton number is the same. Our charge, you can also say, has to be the same. Now here mass number, it does not change because this is 0, so A remains A. Also in this case, because this is electron, so anti-electron neutrino also will be emitted in this case. Now from here what we need to understand, how the proton number is changing in this case. Proton number increases by 1. You see Z plus 1. So this is telling us proton number increases by 1. So this is another point we need to understand. Proton number increases by 1 in beta minus decay. Proton number increases by 1. If we go back to our isotope, we want proton number stays the same. So if there is a 1 alpha decay and 2 beta decays, then proton number will stay same, will not change. Because in this case proton number decreases by 2 and in this case proton number increases by 2. So if we have 2 beta minus decay, 1 alpha decay, so 2 minus 2, it means proton number stays same. So it has to be 1 alpha decay, 2 beta decays. That's the answer for this question. I hope it is clear. I hope this is. So that's the answer. For question 40, it is given that Hadron has a charge of minus E and is composed of 3 quarks. Question is asking us, we need to find out what could be the quark composition of the hadron. Charge on hadron, this is given, so this is very important point. Charge is given to us. Now let's try to understand what is the charge on up quark. The charge on up quark is plus 2 by 3e. The charge on the strange quark, this is minus 1 by 3e. Let me explain to you how to remember the charge on each quark. We have 6 quarks in total in standard model. So let me write down the charge for each quark, and also let me explain to you how you can remember the charge on each quark. First of all, we have up quark. So here we have down quark. So this is down quark. Then we have charm quark. And we have strange quark. So this is strange quark. Then we have top quark and we have bottom one. So this is bottom quark. We can also write down the symbols for them. The symbol for up quark is U and symbol for charm quark is C. Symbol for top quark is T. And the symbol for down quark is T. For strange quark, we use symbol S, and for bottom quark, we use symbol capital P. Now, let's try to understand what is the charge on each quark. If we look at this row, if we look at these 3 quarks, all of them, they have the same charge. They have charge equal to plus 2 by 3e. But if we look at this bottom row, all these 3 quarks, they also have the same charge, that is equal to minus 1 over 3e. So this is very simple way. If you look at up, charm and top, we are talking about something higher, so that's the reason this charge is higher. But when we talk about down, strange, bottom, and we say them, so they sounds like something lower, so that's the reason this charge is lower. So this is one way you can remember that the charge on up, charm and top quark is plus 2 by 3e, and the charge on down, strange and bottom quark, this is minus 1 over 3e. We need to find out the charge on each composition, and then we will compare with the given charge on the hadron. If we look at this one, here we have 3 strange quarks. We need to add the charge on them, or simply we can just multiply with 3, so minus 1 over 3e. If we just multiply, we will get this is equal to minus E. This composition has the same charge as the charge on given hadron. So it means this is correct option, means this is the answer. But let's check the second one. If we look at the second one, B, we can also calculate the charge on this one. So here we have 1 up quark. So up quark has charge 2 by 3e minus we have 2 strange quarks. So we can say 2 times 1 over 3e. So if we add these 2 together, we will get 0. So the charge on this composition is 0, and this is not equal to minus e. So this is not correct option. Now let's look at C now. If we look at C, we have 2 up quarks, 1 strained quark. So the total charge on this composition will be equal to 2 times the charge on up quark. So this is the charge on up quark plus the charge on strained quark. The charge on strained quark is minus 1 over 3e. Now if we add them together, so we have 4, so we will get this is equal to plus e. So this is not equal to minus e, so this is also not correct option. If we look at D now, on D we have 3 up quarks, so the total charge is equal to 3 times the charge on each up quark, means the charge on each up quark. So we can write down this is plus 2 by, this is multiplied by 2 by 3e. So in this case our final answer is plus 2e, and this is not equal to minus e, so this is also not correct option. So the A is the answer. That's the answer. For question 39, it is given to us that a radiation from radioactive source has a range of few millimeters in air and can be deflected by electric field. If it can be deflected by electric field, it means that radiation must have charge. So we can write down it must have charge. So this is the first thing. If you look at these options now, alpha has charge, the charge on alpha particle, this is equal to plus 2e alpha radiation, and the charge on beta minus radiation, this is equal to minus e, and the charge on beta plus radiation, this is equal to plus e. So it means answer can be A, B or C, but gamma, this has no charge. The Q on gamma rays is equal to 0. So it means this is not possible option. So we can just eliminate option D. The second thing it is given to us, the range few millimeters in air. If we look at the range of alpha and beta particles, the range of alpha particle is very short. Alpha radiation, the range of alpha radiation in air is very short, so we can write down alpha radiation range is very short. So its range is very short, few millimeters. Range is very short, so we can write down here range is very short. If we compare with range of beta radiations, mean beta plus or beta minus or beta plus, the range is larger, is longer, so we can say beta radiation, the range is longer. So it means that our best possible option can be A. So that's the answer, because the range of alpha radiation is very short. So that's the answer. Question number 40 is about beta plus decay. Is all about beta plus decay. In order to answer this question, we need to understand beta plus decay. First of all, let's try to understand what is beta plus decay. Beta plus decay. Let's try to write down the equation for beta plus decay. For beta plus decay, let's say we have nucleus X and it decays into another nucleus Y by emitting beta plus particle, beta plus. If this is beta plus, actually beta plus is in fact positron. This particle is positron, and this is antiparticle of electron. So this is antiparticle of electron. So we can write down this is antiparticle of electron. If this is antiparticle, there must be electron neutrino, not electron antineutrino. This has to be electron neutrino. Why it has to be electron neutrino, I will just explain in few seconds. First of all, let's say the atomic number of this one is Z and the mass number of this nucleus is A. So the atomic number of this nucleus has to be Z minus 1, because the atomic number, proton number on both sides has to be the same. So this is plus 1, this has to be minus 1, and mass number, there will be no change in mass number, so this is the mass number. Let me explain to you, if this is antiparticle, why this has to be neutrino. The reason is that the lepton number on both sides has to be conserved. Lepton number, this has to be conserved. So this one has to be conserved. each lepton has a lepton number 1. So let me write down here. Each lepton has lepton number equal to 1. And each antilepton, let me write down, each antilepton has lepton number equal to -1. And if the particle doesn't belong to lepton family, then lepton number will be 0. If you look at this nucleus, this doesn't belong to lepton family, so its lepton number is equal to 0. And this nucleus also does not belong to lepton family. In lepton family, we have 3 neutrinos and we also have 3 particles like electron, muon, and tau, and we have 3 neutrinos: electron neutrino, muon neutrino, and tau neutrino. Those are members of lepton family. This is antiparticle of electron, so its lepton number is -1, and the lepton number of neutrino, this is 1. So that's the reason it has to be neutrino, because lepton number has to be conserved. So simple way to remember is that if this is particle, this has to be antineutrino. If this is antiparticle, this has to be neutrino. So this is the reason. Let's try to answer this question now. For this question, if you look at the first option, if you look at the charge of this one, for any nuclear reaction, charge on both sides has to be the same. Option B, we can simply eliminate. This is not possible because this is anti-neutrino, so this is not possible. And D is also not possible, so we can simply eliminate. So answer is A, or answer is C. First of all, let's look at option A. If you look at the charge on this is plus 2/3. We have 2 down quarks, so the charge on 2 down quarks, this is 2/3e. So it means the net charge on this is equal to 0. But if you look at the net charge here, the total charge, we have 2 up quarks, so this is 2 times 2/3e, plus we have 1/3e. So the total charge on these 3 quarks, this is equal to plus e. And the charge on this beta plus, that is also plus e. And neutrino has no charge. So if you look at this one, the charge on the right side is not equal to charge on the left side. It means this nuclear reaction is not possible. Let's look at C now. We have 2 up quarks, this is 1 down quark. The total charge on this one, this is equal to 1e. You can just calculate. So this is equal to plus e. Now if you look at the charge on 2 down quark, 1 up quark, this charge will be equal to 0. And if you look at the charge on beta plus, this is plus e. And the charge on neutrino, there is no charge. So you see, in this case, charge is also conserved. And this is the possible answer.